Welcome to this SkillPad video resource, where we make learning fun. In this video, we are going to look at the captivating world of magnetism. First discovered in a mineral called magnetite or lodestone, magnets are objects that create magnetic fields, which are invisible forces that not only influence other magnetic objects, but also moving electric charges. Each magnet has two primary areas, known as the north and south poles, where their magnetic force is most potent. An intriguing characteristic of these poles is their interaction. Similar poles repel while different poles attract. The magnetic field surrounding every magnet is a fundamental idea in magnetism. This field is the region around a magnet in which magnetic forces are. These fields are vector quantities, possessing both strength and direction. Understanding these fundamental aspects of magnets and magnetic fields paves the way for delving into more intricate magnetism phenomena. Magnets are basic elements of our world, integral to several technologies we use daily, from electric motors to loudspeakers and computer hard drives, as well as in medical science. Further research into this phenomenon continues to unravel magnetic wonders, such as the levitating bullet train that travels at lightning speeds due to limited friction. Magnetic field lines are a tool to visualize and comprehend the unseen magnetic fields surrounding magnets. They're imagined as continuous closed loops that arise from a magnet's north pole and terminate at the south pole, illustrating the magnetic field's direction. The density of these lines is also significant, with closely packed lines indicating a stronger field and spread out lines revealing a weaker field. This is why the magnetic field is most potent at a magnet's poles, where the lines are most concentrated. The behavior of these lines varies around different objects, such as a plane coil, where they form concentric circles around the wire, or a solenoid, where the lines resemble those of a bar magnet. These invisible lines of force are fundamental in understanding the concept of electromagnetism. The electromagnetic effect of current is the connection between electricity and magnetism. When an electric current passes through a conductor, it generates a magnetic field around itself, which can be visualized as concentric circles with the conductor at the center. The direction of the magnetic field is determined by the current's direction and can be observed through the deflection of a compass needle brought near the conductor. A coil of wire or solenoid, when carrying current, creates a stronger magnetic field, behaving like a bar magnet. The electromagnetic effect is also seen in diamagnetic, paramagnetic, and ferromagnetic materials that react differently in a magnetic field. Thus, a current-carrying conductor is a bridge between electricity and magnetism, and understanding this effect provides insight into the forces that shape our world. Imagine being able to switch a magnet on and off at your convenience. This possible with electromagnets. These unique magnets only exhibit magnetic properties when an electric current is passed through them, similar to chameleons changing their colors. Their strength varies depending on several factors. The more electric current flowing through the wire, the stronger the magnet. The number of turns in the coil also influences the magnetic field's strength, with more turns generating a larger field. Further, the type of material used to make its core also matters, since easily magnetizable materials produce stronger fields. A coil of wire called a solenoid is designed to amplify the magnetic field when current flows through it. This understanding allows the creation of powerful electromagnets used across various fields, from industrial lifting to medical devices. In essence, electromagnets give us control over the magnetic field using electricity, much like possessing a superpower. When a current-carrying conductor encounters a magnetic field, it experiences a force. This effect is determined by Fleming's left-hand rule, known as the motor rule. Here, if your forefinger indicates the magnetic field's direction and the middle finger points to the current's direction, the thumb will demonstrate the force's direction. The magnitude of this force hinges on the strength of the magnetic field, the current volume, and the angle between the current and magnetic field's direction. This phenomenon is fundamental to devices like the electric motor, where a wire coil carrying current placed in a magnetic field spins due to the force exerted. If the direction of the magnetic field or current changes, so does the force's direction. In conclusion, the interaction of electricity and magnetism in a current-carrying conductor placed within a magnetic field leads to the generation of a quantifiable force. Electromagnets are indispensable in our modern lives. They're the driving force behind the ding-dong of doorbells, where a circuit with an iron bar and a small hammer creates a magnetic field, causing the hammer to strike the bell. They're central to DC motors, powering household appliances and toys, with current-carrying coils rotating in a magnetic field. Telephone receivers utilize electromagnets to convert sound waves into electric signals and vice versa, allowing for sound transmission. Likewise, the principle of electromagnetism is used in moving coil loudspeakers to convert electrical signals into the music we enjoy. Lastly, generators, the backbone of our electricity supply, employ electromagnetism to convert mechanical energy into electrical energy. In a nutshell, everything from the chime of a doorbell, a cooling fan, voice transmission, music from speakers, to the electricity in our homes, all rely on the of electromagnets. Switching gears to generation of electricity, ever wondered how electricity is generated using magnetism? This is made possible by a phenomenon called electromagnetic induction, a fundamental principle that powers dynamos, generators, and various everyday devices. In simplest terms, electromagnetic induction involves introducing a conductor, such as a wire, into a changing magnetic field, which causes the wire's electrons to move, thus generating an electric current. The laws proposed by Faraday and Lenz help us understand the magnitude and direction of this induced current. In the case of power generation, a coil of wire is manually rotated within a magnetic field in a generator, inducing current, which we then use to power electrical devices. This principle also applies to dynamos where the coil is spun by mechanical energy. Interestingly, the direction of the current generated changes every half rotation of the coil, hence the term alternating current. From local power plants to bicycle lights, electromagnetic induction is a ubiquitous principle discovered over centuries ago, yet it remains the backbone of our power generation. Fleming's right-hand rule is a fundamental principle in electromagnetism that helps in determining the direction of induced current in a conductor moving within a magnetic field. Named after British scientist John Ambrose Fleming, this rule involves extending your right hand with your thumb, index, and middle fingers all at right angles to each other. Here, the thumb represents the motion of the conductor, the index finger depicts the magnetic field direction, and the middle finger shows the induced current direction. Remember, it's applicable only when the conductor moves perpendicular to the magnetic field. This rule is essential in understanding the workings of generators and the interplay of electricity and magnetism. Its simplicity aids in comprehending complex interactions in electromagnetism, serving as a crucial part of a larger framework of principles and laws governing electrical and magnetic behaviors. Alternating current, or AC, and direct current, or DC, are two fundamental types of electric currents. In DC, electrons flow unidirectionally from the negative to the positive terminal, providing a stable and constant voltage. This type is common in batteries and ideal for devices like laptops and cell phones. Alternatively, in AC, electrons switch their direction back and forth, making it suitable for powering household appliances. The rate of this change in direction, also known as frequency, happens 50 or 60 times per second globally. AC holds a significant advantage for long-distance power transmission, as its voltage can be easily stepped up or down using transformers, leading to minimal power loss. Therefore, AC is used in power grids. Despite their differences, both AC and DC serve unique functions in the world of electricity. Now let's look at how this power gets into our homes. Ever pondered about the journey of electricity from power plants to our homes? Let's credit transformers, the indispensable heart of power transmission. These devices house two wire coils termed primary and secondary, wrapped around a common iron core. Their operation hinges on electromagnetic induction, with a fluctuating magnetic field in the primary coil inducing a current in the secondary coil. Transformers can amplify or diminish voltage by adjusting the number of turns in the coils, crucial for power transmission over vast distances. They ensure the high voltage used for transmission is safely reduced for household usage. However, they do experience losses due to resistance in the coils and the fluctuating field, which, though minimized, can't be fully eradicated. Transformers, in essence, are vital for delivering electricity to our residences. In conclusion, our comprehensive journey through the realm of electromagnetism started with the basic understanding of magnets and their invisible force fields. We learned how these magnetic fields are not only confined to magnets but are a result of moving charges. Our exploration led us to the discovery of how a current-carrying wire can generate a magnetic field, whose strength can be enhanced when coiled into a solenoid, laying the foundation for powerful electromagnets. We also discussed Fleming's left-hand rule, which determines the direction of force in a current-carrying conductor within a magnetic field. Our journey extended to understanding the practical applications of electromagnets in daily life, from doorbells to loudspeakers. We delved into the principle of electromagnetic induction and its role in the functioning of dynamos and generators, and comprehended the laws of electromagnetic induction, Faraday's and Lenz's. We also distinguished between alternating and direct current and their conversion processes. We acknowledged the benefits of alternating current for efficient power transmission, and concluded our journey with a look at transformers, the key components of our power grids. Finally, we reminded you of the omnipresence of electromagnetism in our daily life, from flipping a light switch to the ringing of a doorbell. Thank you for using this SkillPad video resource. We hope it was insightful. Tag along as we delve into the world of science for your learning pleasure. We hope to see you again soon.